The familiar stars above are not permanent. In about 4.5 billion years, our Milky Way galaxy will begin an inevitable, majestic collision with the Andromeda galaxy. This is not a story of science fiction, but a future written in the motion of the stars themselves. By the end of this exploration, you will understand exactly what this cosmic merger means for our solar system and the ultimate fate of our night sky. We will uncover how scientists know this with certainty and what spectacular transformations await our galactic home. What does it feel like to witness the end of a galaxy you call home? To truly grasp the scale of this future event, we need to know the characters involved. Our home, the Milky Way, is a grand cosmic pinwheel, a barred spiral galaxy. Picture a vast, slowly turning disk of starlight, dust, and gas, measuring an almost incomprehensible 100,000 light-years from edge to edge. Within that disk, our solar system is nestled in a quieter region, a galactic suburb known as the Orion Arm. From our vantage point, the Milky Way appears as a pale, shimmering river of light arching across the night sky, but this is merely our view from within the disk. For most of human history, this was thought to be the entire universe, our destined partner and our greatest rival in size within our local group of galaxies is the Andromeda Galaxy, catalogued as M31. It is the most distant object you can see with your unaided eye on a clear, dark night, appearing as a faint, elongated smudge of light. For centuries, astronomers classified it as just a nebula, a cloud of gas within our own Milky Way. That all changed in the 1920s when the astronomer Edwin Hubble made a historic discovery. By observing a special kind of star within Andromeda, a Cepheid variable, he was able to measure its staggering distance. He proved it was not a part of our galaxy, but an island universe of its own, lying a monumental 2.5 million light-years away. This single observation shattered the old cosmic model and revealed a universe filled with galaxies. When we compare the two, Andromeda is the larger and more massive contender. It spans about 220,000 light-years across, significantly wider than our Milky Way. It also contains roughly 1 trillion stars, compared to our galaxy's estimated 2 to 400 billion. Both are spiral in shape, but Andromeda's structure is more classic and pronounced, with tightly wound arms glowing with the light of countless stellar nurseries. Our Milky Way has a distinct central bar, a thick structure of stars from which its spiral arms emerge. Despite its greater size, Andromeda may not be the densest, as much of its mass is spread out in a vast, diffuse halo of dark matter, an invisible gravitational glue that holds galaxies together. Understanding these individual traits, their sheer scale and composition, is the first step in forecasting what happens when two such titans are drawn into a gravitational dance from which there is no escape. That faint smudge of light in Andromeda holds a secret within its glow, a clue written not in words but in color. The light from any star or galaxy can be stretched or compressed depending on its motion relative to us, an effect known as the Doppler shift. You experience a version of this when a siren changes pitch as an ambulance speeds past you. As it approaches, the sound waves are compressed, creating a higher pitch. As it recedes, the waves are stretched, creating a lower pitch. Light behaves in a similar way. When a celestial object moves away from us, its light is stretched toward the red end of the spectrum, a redshift. When it moves toward us, its light is compressed, shifting toward the blue. For nearly a century, astronomers have meticulously analyzed the light from the Andromeda Galaxy. The finding was definitive and profound. Unlike almost every other galaxy we observe, which shows a redshift as the universe expands, Andromeda's light is blue-shifted. This single, measurable fact tells us it is on a direct course for us, moving closer with every passing second. The current best measurement puts its approach speed at about 110 kilometers per second, a velocity so immense it could cross the entire United States in less than a minute. But this discovery alone wasn't enough to predict a collision. Speed tells you how fast something is moving, but not its exact trajectory. To know if we were destined for a direct hit or a near miss, scientists needed a third dimension of data. They needed to know not just if Andromeda is moving toward us, but how it is moving sideways. This side-to-side motion, called proper motion, is incredibly difficult to measure for an object so distant. It's like trying to discern the sideways crawl of a snail on the horizon from thousands of miles away. The breakthrough came from a decade-long project using the Hubble Space Telescope. By repeatedly observing extremely stable, bright stars within Andromeda over many years, astronomers were able to detect an almost imperceptible drift. They pinned down that subtle sideways motion. When they combined this data with the blue shift and our precise knowledge of the distance between the galaxies, they could plot the future course with unprecedented accuracy. The result of these painstaking calculations was the cosmic forecast we now accept as fact. The Milky Way and Andromeda are not on a glancing path. They are aimed almost directly at each other's centers, locked in a gravitational embrace that began eons ago. This certainty transforms the event from a celestial what-if into an inevitable chapter of our galaxy's story, written in the silent language of light and motion. With a collision confirmed, the next question becomes far more dynamic. What does a crash between galaxies actually look like? This painstaking measurement of sideways drift was the final piece of the puzzle. For years, astronomers knew Andromeda was approaching, but its precise trajectory remained a mystery. Was it a direct bullseye aimed at our galactic core, or a graceful cosmic flyby? The Hubble Space Telescope provided the answer by focusing on a fixed point in the sky, using distant quasars as a stationary backdrop. These quasars are so immensely far away they appear as unmoving reference points. By comparing Andromeda's position against these celestial signposts year after year, scientists detected an almost unbelievably tiny shift. It was the astronomical equivalent of measuring the growth of a human hair from a distance of 100 miles. This minuscule wiggle, when combined with the known approach speed, allowed astronomers to plot a full three-dimensional map of Andromeda's motion through space. The landmark study, published in 2012, delivered a definitive forecast. The galaxies are not on a perfect head-on collision course, but something even more fascinating. They are destined for a glancing, complex interaction, a gravitational sideswipe that will initiate a billion-year-long dance. This work transformed a centuries-old curiosity into a precise, data-driven prediction of our galaxy's future. To comprehend such a future, we must first grapple with the timescales involved. 4.5 billion years is a number that defies human comprehension. To truly feel the weight of that time frame, let us shrink the entire history of our planet down to a single, familiar calendar year. On this cosmic calendar, Earth forms at the stroke of midnight on January 1st. The first simple life emerges in the oceans by late March. Dinosaurs rule the land in mid-December, only to vanish on the morning of December 26th. All of recorded human civilization, every empire and invention, every story ever told, fits into the final minute before midnight on December 31st. Now extend that timeline. The collision with Andromeda is not an event on this calendar year. It is an appointment scheduled for late August of the next year. This staggering perspective shows we are living in the opening moments of an epic that will unfold over epochs we can scarcely conceive. It also means our own sun has its own, more imminent destiny. Long before the galactic merger reaches its climax in roughly 5 billion years, our sun will exhaust its core hydrogen fuel. It will swell into a red giant, its outer layers likely engulfing the inner planets, before eventually shedding its outer shell and leaving behind a cooling white dwarf core. This stellar transformation is a separate, profound story for our solar system, running on a parallel clock to the galactic dance. So, while the main event between Milky Way and Andromeda is inevitable, it is also incredibly distant. For now, we are simply observers of the first slow motions. The approach has already begun. The first close pass will be a spectacle of cosmic choreography, not a cataclysm. In roughly 4.5 billion years, the outer halos of dark matter surrounding our Milky Way and Andromeda will begin to touch. Think of these halos as vast, invisible spheres of gravitational influence, stretching far beyond the visible starlight. This initial contact is the starting bell for a dance that will last for billions of years. The galaxies will not collide head-on like two solid objects. Instead, they will swing past each other in a gravitational arc, a cosmic near-miss that will permanently alter them both. The sheer force of their mutual gravity during this pass will act like a colossal, invisible hand, reaching into each galaxy and pulling. Long, brilliant ribbons of stars, gas, and dust will be drawn out into intergalactic space, forming structures known as tidal tails. These luminous streams will arc away from the galactic cores, resembling the spiraling water from two sprinklers spinning past one another. For any hypothetical civilization witnessing this from within the disk of the Milky Way, the night sky would begin an irreversible change. The familiar band of our own galaxy would be joined and then utterly dominated by the approaching form of Andromeda. It would no longer be a faint smudge. It would swell into an immense, detailed structure of spiral arms, filling a quarter of the sky, then half, its light washing out the fainter stars of our own celestial neighborhood. This first encounter is a gravitational slingshot. The galaxies will swing past, stealing orbital energy from each other, which ensures they cannot escape. They will loop out slow and be pulled inexorably back for a second, closer pass. This initial act is merely the opening movement in a symphony of merging, a prelude to the true union that will forge an entirely new kind of galaxy. Our solar system's journey through this merger is one of profound relocation, not annihilation. The vast emptiness of space is the key to our survival. Within a galaxy, stars are not packed together like grains of sand on a beach. They are more like a few isolated fireflies scattered throughout an entire, darkened stadium. The average distance between stars in our galactic neighborhood is about 4 light-years. That is 25 trillion miles of nothingness. When the two galaxies intermingle, their stars will pass through each other's spaces like two swarms of bees merging, where each individual bee has miles of empty air around it. Sophisticated computer simulations of the merger, which model the gravitational pull of hundreds of billions of stars and immense halos of dark matter, consistently show the same outcome. The probability of any two stars colliding directly is vanishingly small, almost zero. Our Sun, with its family of planets, will not be struck. Instead, it will be caught in the immense gravitational tides of the merging giants. We will likely be flung onto a new, wider orbit, a cosmic passenger relocated to the outskirts of the newly forming galaxy. This gravitational turbulence, however, is not without side effects. The most significant local danger comes not from other stars, but from our own solar system's distant frontier. Far beyond the orbit of Pluto lies the Oort cloud, a vast, spherical shell of icy planetesimals held in a loose gravitational embrace by the Sun. This reservoir is the source of long-period comets. The gravitational jostling from the merger could act like a tremor through this cloud, dislodging countless icy bodies and sending a potential shower of comets spiraling inward. For a living world, this could pose a serious hazard. Yet, for Earth, this point is largely academic. The galactic merger reaches its climax in 4 to 5 billion years. Our own star has a different schedule. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin to swell into a red giant star. Its outer layers will expand, likely engulfing the orbits of Mercury and Venus and rendering Earth utterly uninhabitable, its surface scorched and transformed long before the galaxies complete their final union. So, while our solar system may sail through the merger safely, any witnesses to the celestial spectacle will not be human as we know ourselves today. They would be descendants existing in a form and place we cannot foresee, observing a transformed sky from a new home. This realization shifts our perspective from a personal fate to a galactic one, focusing on the ultimate legacy of the merger itself. What final form will this billion-year dance create? The sheer emptiness of a galaxy is its most protective feature. This vastness is why, despite the dramatic term collision, the hundreds of billions of stars within the Milky Way and Andromeda will almost never physically meet. Space is so profoundly empty that if you reduced our Sun to the size of a single grain of sand, the nearest star, Proxima Centauri, would be another grain over 4 miles away. Now picture two entire galaxies, each with that same incredible emptiness, passing through one another. The stars are like those isolated grains separated by miles, simply drifting past on new, altered paths. The real fireworks of a galactic merger come from a different source entirely, from the thin veils of material that do fill the spaces between those stars. We call this the interstellar medium, a sparse mixture of gas, mostly hydrogen, and fine dust. While it accounts for only a small percentage of a galaxy's mass, this diffuse material is the key to the merger's most visible spectacle. When the galaxies intermingle, these immense clouds of gas and dust are not like stars that can slip past each other. They are tangible, fluid structures. As the galaxies swing by, their gravitational forces slam these clouds together at incredible speeds. This collision is a violent, transformative event. The gas clouds compress, they shock, they heat up, and under that tremendous pressure they collapse. These collapsing pockets become the nurseries for a new generation of stars. A galactic merger, therefore, is not a story of destruction, but one of furious, brilliant creation. Astronomers call this a starburst, a sudden and intense wave of star formation that can outshine the combined light of the parent galaxies. The merged galaxy becomes adorned with dazzling blue clusters of massive, hot, young stars, their intense radiation causing surrounding gas to glow in vibrant pinks and reds. This cosmic renaissance is the true legacy of the collision, painting the merging entity with the brushstrokes of new light. Yet, this burst of birth is only one phase in a much longer transformation. While the stars glide past in silence, the gas clouds face a far more violent destiny. These immense reservoirs of hydrogen, the raw material for building new suns, are not isolated points like stars. They are sprawling, nebulous structures that fill the spaces between them. When the galaxies swing together, these clouds cannot simply pass through one another. They are tangible, fluid entities, and their collision is where the real cosmic drama unfolds. Picture two vast, misty atmospheres smashing together at hundreds of kilometers per second. The leading edges of these clouds meet with unimaginable force, creating shock waves that ripple through them like sonic booms in slow motion. This sudden, violent compression is a trigger of epic proportions. It squeezes the gas, heating it and forcing countless pockets to collapse under their own gravity. In a stable galaxy like our Milky Way today, star formation is a slow, steady process. But in the heart of a galactic merger, it becomes a frenzy. The rate of new star birth can skyrocket, not by a little, but by a factor of 100 or even 1,000. This explosive period is what astronomers call a starburst. The result is a transformation of light and color across the merging galaxies. Regions that were once dark lanes of dust become incandescent stellar nurseries. blazing with the intense blue glow of massive newborn stars. These are the O-type and B-type stars, behemoths dozens of times more massive than our Sun. They burn their nuclear fuel with a desperate intensity, living for only a few million years, a mere blink on cosmic timescales. Their brilliant, short lives end not with a whisper but with a cataclysm. They die in spectacular supernova explosions, scattering newly forged heavy elements like carbon, oxygen, and iron back into the surrounding gas. This enriched material will one day coalesce into new stars, planets, and perhaps, in the distant future, the building blocks of life elsewhere. For now, it seeds the chaos with the chemistry for future worlds. We do not have to imagine this chaotic, beautiful phase. Telescopes have given us a front-row seat to similar mergers happening right now in the distant universe. Galaxies like the Antennae galaxies, a pair of spirals caught in a mid-collision embrace, show us the template. Their shapes are distorted into long, luminous tidal tails, and their cores are pockmarked with the brilliant pink glow of ionized hydrogen, a telltale sign of intense star formation. The blue clusters speckling their structures are those very nurseries, the signature of the starburst in action. This is the fate that awaits the Milky Way and Andromeda, a temporary but magnificent era where the merged galaxy will shine with a ferocious blue light, a cosmic renaissance written in fire and gas. Yet, such a furious output of energy cannot be sustained. The starburst phase, for all its brilliance, is inherently self-limiting. It is a feast that quickly consumes the banquet. Those massive blue stars die young, and their violent supernova can actually blow the remaining gas away, preventing further collapse. The very process of frenzied star formation exhausts the available fuel. After several 100 million years of this stellar fireworks display, the gas reservoirs are depleted, scattered, or heated to such a degree that they can no longer easily collapse. The brilliant blue clusters fade as their massive stars expire, and the rate of star formation plummets back to a quiet trickle. The merger leaves behind a galaxy that has spent its primary fuel supply in a single, glorious burst. What remains is a system entering a long, quiet autumn, its structure forever altered by the dance. This gas crisis leads to the final, enduring form of the merged galaxy, a shape that is both an ending and a new beginning. The Starburst Era will be a time of breathtaking, violent beauty for the merged galaxy. For several 100 million years, this new system, sometimes called Milkdromeda, will transform into a cosmic foundry of unparalleled activity. The immense gas clouds compressed during the close passes will ignite not with isolated sparks, but with a continent-sized wildfire of star birth. Across the galactic landscape, thousands upon thousands of stellar nurseries will blaze to life. These are not the quiet, long-lived stars like our Sun. The extreme pressures and densities within these collapsing clouds favor the creation of stellar giant stars dozens, even hundreds of times more massive than our own. These are the blue supergiants, cosmic furnaces that burn with a ferocious intensity. Their brilliance is matched only by their brevity. While our Sun will shine steadily for over 10 billion years, these massive stars live fast and die young, exhausting their nuclear fuel in a mere few million years. Their entire lifespan is a fleeting moment on the galactic clock, a short, spectacular flash. Their deaths are where the true alchemy happens. A star like our Sun ends its life relatively quietly, gently puffing away its outer layers. But a massive star meets a far more dramatic fate. When its core can no longer support itself against its own immense gravity, it collapses in a fraction of a second and then rebounds in a cataclysmic explosion, a supernova. For a brief time, a single dying star can outshine the combined light of an entire galaxy. Within that unimaginable inferno, atomic nuclei are smashed together under extreme temperatures and pressures, forging elements that ordinary stellar fusion cannot create. This is the cosmic forge where the iron in your blood, the gold in a ring, and the uranium deep within the Earth were originally synthesized. Each supernova is a scattering event, hurling these newly minted heavy elements back into the surrounding interstellar medium. Over this era, the galaxy's gas becomes progressively enriched, seeded with the complex chemistry necessary for rocky worlds and the potential for biology. This starburst phase, therefore, is not just a light show. It is an essential period of galactic recycling and chemical maturation, setting the stage for a more diverse future. Yet, such furious creation is inherently unsustainable. The very process acts like a wildfire consuming its own fuel. The supernova explosions, along with powerful stellar winds from the massive stars themselves, begin to violently blow the remaining gas away, heating it and preventing further collapse. The galaxy, having spent its primary reservoir of star-forming material in a single, glorious burst, gradually quiets. The brilliant blue clusters fade as their massive stars wink out, one by one, in final, glittering flashes. The frenzy subsides, leaving behind a galaxy profoundly changed, not just in shape, but in its very elemental composition. It enters a long, quieter era, its structure settling into a form that reflects the totality of the epic collision. The beautiful spiral arms we know are not permanent structures. They are temporary patterns like ripples on a pond, and the gravitational turmoil of the merger will erase them completely. As the Milky Way and Andromeda swing past each other again and again over the next 1 to 2 billion years, their mutual gravitational pull acts like a pair of immense, invisible hands. These hands reach into the orderly disks of both galaxies and begin to knead them. Stars that once traced graceful, circular orbits around their galactic centers are now subjected to conflicting tugs. Some are pulled inward, others are flung outward onto vast, looping paths that carry them high above the galactic plane. The thin, flat disk, a structure that took billions of years to form, becomes puffed up and scrambled. The distinct spiral patterns, those grand designs of density waves and star formation, are the first features to vanish. They are smoothed away into a growing haze of stellar motion. This transformation is not a gentle reshaping. It is a fundamental reorganization of an entire galactic architecture. To visualize it, think of two distinct swirls of cream in a cup of coffee. For a moment, you can see each spiral clearly, but then you stir. The spoon's motion introduces chaos, pulling the once separate patterns into one another until they blend into a uniform tan mixture. The gravitational tides of the merger are that cosmic spoon, and the stars are the cream. The beautiful, two-dimensional pinwheels are stirred into a three-dimensional cloud. This new structure will be elliptical in shape, a vast football of stars orbiting in every direction. There will be no clear disk, no spiral arms, no lanes of dark dust. The night sky for any world within it would be transformed. Instead of a dominant band of starlight crossing the heavens, the sky would be filled with a relatively even, diffuse glow in all directions, punctuated by the brilliant clusters of the merger's final stellar generations. This elliptical galaxy is the inevitable and lasting monument to the collision, the final form of the combined system we call Milkdromeda. It represents a quieter, more settled chapter in galactic life. The final product of this billion-year dance is a galaxy transformed beyond recognition. Astronomers, with a touch of poetic license, have named this future entity Milkdromeda, or sometimes Milkdromeda. It will bear little resemblance to the elegant spirals that birthed it. Instead, the most likely outcome is a giant elliptical galaxy. Picture not a spinning disk, but a vast, three-dimensional swarm, a cloud of stars shaped like a colossal football or an egg. Within this form, stellar orbits are not aligned in a single plane. They are chaotic, with stars moving in every direction, like a hive of bees with no central comb. There is no thin disk, no spiral arms, no dark lanes of dust. the night sky from within Milkdromeda would be utterly alien. The heavens would glow with a relatively uniform, diffuse light in all directions, a soft, omnipresent stellar haze replacing the familiar river of the Milky Way. This elliptical form is the signature of a mature, settled galaxy, the quiet aftermath of a violent merger. It is often described by a simple, poignant phrase, red and dead. The red refers to its dominant color. The furious starbursts of the merger consumed the available gas in a brilliant, blue firestorm. With that gas depleted or blown away, star formation grinds to a near halt. The massive, hot, blue stars die off quickly, leaving behind the longer-lived, cooler, redder stars, the aging population of both original galaxies. Their collective glow gives the entire galaxy a warmer, reddish hue. The dead denotes not an absence of stars, but an absence of stellar birth. It is a galaxy that has largely finished its major period of construction, entering a long, stable autumn where change happens on timescales far too slow for any civilization to perceive. This will be the new, permanent home for the combined hundreds of billions of stars from the Milky Way and Andromeda, a cosmic monument forged from two distinct histories. Yet, even as Milkdromeda settles into its eons of quiet, the story of our local group of galaxies is not over. There is another player in this cosmic neighborhood, one whose own fate is now inextricably linked to the new giant in its midst. Our story of two giants has a smaller yet vital third character. While the Milky Way and Andromeda dominate the local group, the Triangulum galaxy, known as M33, is a key participant in this cosmic ballet. It is the third largest galaxy in our neighborhood, a perfect spiral much smaller than its massive companions, but still home to tens of billions of stars. For a long time, its role was unclear. Was it a distant, independent island, or was it gravitationally tied to the unfolding drama? Recent observations have provided a compelling answer. The Triangulum galaxy is not a free agent. Precise measurements of its motion reveal it is likely in a long, looping orbit around the Andromeda galaxy, a distant satellite caught in its immense gravitational pull. This means that as Andromeda marches toward us, it is not coming alone. It brings with it an entire entourage with Triangulum as its most prominent companion. This changes the simple narrative of a two-galaxy collision into a far more complex, three-body gravitational puzzle. Computer simulations that model the future of our local group must now account for this third player, and the possibilities are fascinatingly uncertain. The gravitational tides during the close passes between the Milky Way and Andromeda will send powerful ripples through the entire system. One scenario suggests that Triangulum, already orbiting Andromeda, could be drawn inward by the chaos. It might merge with Andromeda before Andromeda fully merges with us, essentially becoming a part of the giant that then collides with the Milky Way. Alternatively, the gravitational slingshot effect could work in the opposite direction. A precise gravitational kick during the main merger could fling the smaller Triangulum galaxy clear out of the system entirely, sending it on a lonely journey into intergalactic space, a cosmic billiard ball shot away from the wreckage. The most likely outcome, however, may be a patient, drawn-out finale. Triangulum could survive the initial merger chaos, continuing its orbit around the new Milkdromeda galaxy for many more billions of years, only to slowly spiral in and merge with the elliptical giant in a distant secondary act. This intricate dance reminds us that the universe rarely deals in simple duets. Cosmic interactions are almost always complex ensembles. The fate of Triangulum adds a layer of beautiful uncertainty to the forecast, a reminder that while we can predict the broad strokes of galactic evolution, the precise choreography of individual dancers remains partly unknown. Yet this local drama is not unique. It is a single, nearby example of a universal process unfolding across the cosmos, a fundamental mechanism that has shaped the universe we see today. The collision that awaits us is not a cosmic anomaly, but a universal rite of passage. Galaxy mergers are a fundamental part of how the universe builds and evolves its largest structures. To our ancestors, the night sky seemed eternal and unchanging, but the deeper truth revealed by modern telescopes is a cosmos in constant, dynamic interaction. The Hubble Space Telescope, peering back across billions of years, has shown us that in the early universe, when galaxies were closer together, such collisions and mergers were commonplace, even dominant. This was the era of galactic assembly, where smaller building blocks clumped together to form the majestic spirals and ellipticals we see today. Our own local event is simply a late chapter in this ongoing story, a final consolidation happening long after the universe's most frenetic period of construction has passed. Remarkably, we don't have to look to the distant past or future to see evidence of this process. Our very own Milky Way is a living archive of its own violent history. It did not form in pristine isolation. Detailed surveys of stellar motions, particularly from the European Space Agency's Gaia mission, have uncovered ghostly signatures of ancient mergers right here at home. One of the most dramatic is known as the Gaia sausage Enceladus, the remnant of a dwarf galaxy that collided with the young Milky Way perhaps 10 billion years ago. The stars from that long-vanished companion were not destroyed. Instead, their orbits were scrambled, and they now form a distinct sausage-shaped distribution within our galaxy's halo, a fossilized imprint of a past feast. Our galaxy's halo is littered with such stellar streams and clusters, the celestial archaeology of smaller galaxies consumed over eons. We are, in a very real sense, the product of collisions. To visualize our own future, we have cosmic laboratories millions of light years away. The Antennae galaxies are a pair of spirals caught in a mid-collision embrace, their long, luminous tidal tails resembling an insect's antennae. In their distorted cores, we see the brilliant pink glow of ionized hydrogen, a telltale sign of the intense starburst activity triggered by the merger. The blue speckles across their bodies are clusters of newborn, massive stars, shining with ferocious intensity. This is the template. This is the phase of furious creation and dramatic reshaping that the Milky Way and Andromeda will enter. By studying systems like the Antennae, astronomers can calibrate their computer models, testing the physics of gravity, gas dynamics, and star formation against real-world examples. These observations provide the crucial data that refine the simulations, giving us increasing confidence in the forecast for Milkdromeda. It transforms a theoretical prediction into an observed inevitability, a future we can already see playing out across the universe. This grand perspective shifts our place in the narrative from isolated spectators to participants in a universal cycle of creation and transformation, a cycle that has shaped everything we see in the night sky. The intricate forecast of Milkdromeda is not born from guesswork, but from a symphony of mathematics and silicon. To peer billions of years ahead, astronomers rely on the immense power of supercomputers, running what are known as n-body simulations. The challenge is staggering. You must model the gravitational dance of hundreds of billions of individual stars, each pulling on every other, across a time span longer than the current age of our planet. Doing this directly is impossible for even the fastest machine, so scientists use a brilliant shortcut. In these simulations, each particle does not represent a single star, but a massive collection of them, a swarm of millions of suns bound together by their shared gravity. The supercomputer's task is to calculate the pull between every single one of these swarms for every tiny step forward in simulated time. It is a problem of almost unimaginable scale, requiring thousands of processors to work in concert for months. Projects like the Illustris TNG simulation and those from the University of Zurich have done exactly this, creating virtual universes where galaxies like our own are set on a collision course. The results are those stunning visualizations we see: the graceful arcs of tidal tails, the slow puffing of spiral disks into elliptical clouds. They are not perfect one-to-one predictions of the future. Small uncertainties in our present-day measurements, like the precise sideways motion of Andromeda or the total amount of invisible dark matter, mean the simulation can produce a range of probable outcomes. Yet across all these runs, the core narrative remains unshaken. The merger is certain and its general shape is clear. This is how raw data, blue shifts, proper motions, mass estimates, is woven into a coherent visual story of our galactic fate. These digital laboratories do more than show us what will happen. They reveal the invisible architect guiding every single step of the process, a hidden component that holds the entire cosmic drama together. The true choreographer of this cosmic dance is completely invisible. Every stunning simulation, every precise prediction of the merger's timeline, depends on a hidden framework that outweighs all the stars and gas we can see. This is the realm of dark matter, the unseen sculptor that holds galaxies together and dictates their every move. While the luminous spiral arms and glowing nebulae capture our attention, they represent less than 15% of the total mass of a galaxy like the Milky Way. The overwhelming majority, roughly 85%, is composed of this mysterious substance that does not emit, absorb, or reflect light. We cannot see it with any telescope, yet we know it is there because of its immense gravitational influence. It is the dark matter halo, a vast spherical cloud that envelops each galaxy, extending hundreds of thousands of light years beyond the visible edge. This halo is the true gravitational anchor, the deep well that stars and gas orbit within. When we speak of the Milky Way and Andromeda beginning their merger in 4.5 billion years, we are not timing it by when their stars grow close. We are timing it by when these two immense, invisible halos first begin to touch and overlap. They will interpenetrate long before the stellar disks do, their gravity weaving together to create a single, combined gravitational landscape. The visible galaxies, all the stars and nebulae we cherish, are merely following the contours of this pre-established terrain, like leaves floating on the surface of a swirling, invisible current. This means the most decisive phase of the collision happens in complete darkness, a silent gravitational handshake that sets the stage for all the visible fireworks to come. Our ability to forecast the merger with such confidence is a testament to our growing, if indirect, understanding of dark matter's rules. By observing how stars move at the outer edges of galaxies, where visible matter is sparse, astronomers can map the shape and strength of this invisible grip. These observations feed directly into the supercomputer models, allowing them to simulate how such halos interact. Without accounting for dark matter, the galaxies would simply pass through each other with far less dramatic consequence. It is the combined gravitational pull of these massive halos that drains the orbital energy from the two systems, ensuring they fall back together and ultimately merge. So, while we watch for the brilliant starbursts and tidal tails, we are really witnessing the aftermath of a decision made in the dark. This profound reliance on the invisible challenges our perception of the cosmos, reminding us that the universe is governed not only by what shines, but overwhelmingly by what remains hidden in plain sight. Deep within the heart of every major galaxy lies an unimaginably dense anchor. Our Milky Way is no exception. At its core, 26,000 light-years away, sits Sagittarius, a star, a supermassive black hole with a mass 4 million times that of our Sun. Andromeda harbors its own colossal counterpart, known as M31 star, a behemoth estimated to be 100 million solar masses. These invisible giants are not passive spectators to the galactic merger. They are central characters with their own dramatic finale. As the stars and dark matter of the two galaxies intermingle and settle into the new elliptical shape of Milkdromeda, these black holes will begin a slow, inevitable descent. They are drawn downward not by a simple pull, but by a fascinating process called dynamical friction. Picture each black hole moving through a dense sea of stars. As it travels, its immense gravity tugs on the surrounding stars, pulling them slightly toward it. This creates a wake of slightly denser material behind the black hole, like the trailing wave behind a boat. That wake, in turn, exerts a gravitational drag on the black hole itself, sapping its orbital energy. Over hundreds of millions of years, this relentless friction will cause both Sagittarius, a star, and M31 star to sink toward the very center of the new galaxy. There they will find each other. The two supermassive black holes will become gravitationally bound, forming a binary pair locked in a final, intimate dance. They will orbit one another at a staggering pace, separated by a distance smaller than our solar system. This binary phase is a prelude to the ultimate union. As they circle, they will churn the fabric of spacetime itself, emitting ripples known as gravitational waves. These are not waves of light or sound, but literal distortions in the geometry of the universe, predicted by Einstein's theory of general relativity. The energy lost to these waves causes the black holes to spiral ever closer, their orbits tightening like a slowing whirlpool. For eons, this spiral continues, a silent, invisible waltz in the dark. The final act is one of cosmic violence and profound silence. When the black holes are close enough, they will merge into a single, even more monstrous black hole, with a combined mass of over 100 million suns. In the last few moments before they become one, their orbital speed will approach a significant fraction of the speed of light, and the intensity of the gravitational waves they emit will spike. A final titanic burst of these spacetime ripples will be unleashed, carrying away energy equivalent to the light of billions of galaxies for a brief instant. This signal will propagate outward in all directions, a faint whisper traveling across the universe for billions of years. For any civilization with the technology to listen, this gravitational wave chirp would be the definitive signature, the final stamp confirming the merger of two galactic hearts is complete. It marks not an end but a new beginning for the quiet, elliptical galaxy now anchored by a single, silent giant. The most profound change would be the vanishing of the Milky Way itself. For billions of years, that pale, familiar river of light has been a constant in Earth's night sky, a celestial landmark woven into countless human stories. During the merger, that band would not simply fade. It would be torn apart, its structure dissolved by the immense gravitational tides. The orderly spiral that gave our galaxy its name would be stirred into chaos, its stars scattered into a new, three-dimensional configuration. From our vantage point within that chaos, the distinct band would blur, then dissolve entirely, replaced by a sky of overwhelming and unfamiliar detail. Instead of a single luminous path, the entire heavens would glow with a soft, diffuse light, a blended haze from hundreds of billions of stars now orbiting in every direction. This new sky would have no clear orientation, no galactic north or south. It would be a dome of uniform stellar density, a constant, gentle reminder that the old cosmic order is gone forever. Within that haze, brilliant points of violent creation would shine. Vast nebulae, glowing pink and red from the radiation of newborn stars, would appear as sprawling clouds far larger than any in our current sky. The blue-white fire of young stellar clusters, the remnants of the great starburst, would speckle the darkness like scattered diamonds, and occasionally a new point of light would flare with terrifying brilliance, a supernova from a dying giant star, outshining everything else for weeks before fading away. These would not be rare events, but regular celestial fireworks in the active heart of Milkdromeda. Most strikingly, there would be no target to point to and call Andromeda. The galaxy that was once a distinct, fuzzy patch would have swollen to encompass the entire sky, its structure fully merged with our own. The concept of two separate galaxies would be a forgotten piece of ancient astronomy, a fact known only from data records, not direct experience. For any observer, the sky would simply be the sky, a magnificent and unified whole born from collision. This celestial metamorphosis represents the most dramatic visual change to our planet's heavens since its formation. It is a direct, humbling illustration of cosmic impermanence, showing that even the grandest structures we consider permanent are merely temporary patterns in an endless dance of gravity and time. The sky itself becomes a history book, its every star a sentence in the story of a merger that reshaped a local universe. The creation of Milkdromeda is not the end of our cosmic story, but a new chapter in a much larger volume. This colossal elliptical galaxy will become the gravitational centerpiece of our entire local group, a collection of over 50 galaxies bound together by their mutual pull. For now, this group is a loose archipelago with the Milky Way and Andromeda as its two dominant islands. Their merger will consolidate the vast majority of the group's visible mass into one single, commanding entity. What then becomes of the other inhabitants, the dozens of smaller dwarf galaxies that currently orbit the two giants? Their fate is one of gentle assimilation or perpetual companionship. Galaxies like our own nearby satellites, the Large and Small Magellanic Clouds, those fuzzy patches visible from the southern hemisphere, are already caught in our galaxy's gravitational grip. Over the eons following the main merger, they will likely be slowly drawn into Milkdromeda itself, their stars adding to the great elliptical swarm in a series of minor, final accretions. Other, more distant dwarfs may avoid this fate, instead settling into long, stable orbits around the new galactic giant, becoming permanent moons in its immense halo. This process transforms our local group from a collection of distinct entities into a unified kingdom, with Milkdromeda as its sovereign. This consolidation has a profound, almost philosophical consequence for the very distant future. We live in an expanding universe where the space between galaxies is continuously stretching. On the scale of our local group, gravity is strong enough to overcome this expansion. That's why we are destined to collide with Andromeda. But for galaxies outside our local group, the expansion wins. Over timescales that dwarf even the age of the universe itself, hundreds of billions of years from now, this relentless expansion will carry every other galaxy cluster away from us. They will recede faster than light can travel, vanishing beyond a cosmological horizon. What will remain from our vantage point within Milkdromeda, an island? Our local group, having merged into one vast red elliptical galaxy, will float in an ocean of unimaginable blackness. The night sky, which once held the faint smudges of distant galactic cities, will become utterly, profoundly dark. No new galaxies will be visible. All evidence of the larger cosmos will have disappeared, leaving future astronomers with a sky containing only the stars of their own isolated galaxy. The merger we've detailed is therefore more than a spectacular local event. It is a decisive step toward that ultimate, quiet isolation. It is the process by which our corner of the universe prepares for the long solitude ahead, gathering its material into one final, unified form before the curtain of expansion falls on the rest of the cosmic stage. That future of profound isolation is built upon processes we can describe with mathematics, yet their scale remains almost impossible to truly feel. To bridge that gap, let's shrink the cosmic drama down to a scene we can walk through in our minds. Picture two immense, glowing metropolises, each home to hundreds of billions of inhabitants. These are not cities of brick and steel, but cities of light, where every inhabitant is a star. They are separated by a vast distance, 1,000 miles of perfect, empty plain. Now, set these two celestial cities in motion, sliding toward one another with an eerie, frictionless grace. This is the approach of the Milky Way and Andromeda. When they finally meet, the most counterintuitive part of the merger unfolds. The skyscrapers, the buildings themselves, do not crash. They are the stars, and each is separated by miles of vacant space. They simply glide past one another, their paths altered by a distant mutual pull, but their structures intact. The real collision happens in the atmosphere of the cities. It's in the parks, the open squares, the morning fog, and the suspended dust. This is the interstellar gas and dust that fills the voids between the stellar structures. When the cities interpenetrate, these diffuse atmospheres slam together. The fog compresses, the dust clouds ignite, and in countless locations across the merging metropolis, brilliant, localized fireworks erupt. These are the stellar nurseries, the bursts of new star formation, blazing to life not from crashing buildings, but from colliding air. Over eons, the two distinct street grids are stirred together by invisible forces. The orderly layout of each original city dissolves into a new, more three-dimensional and blended design. The final result is not two cities side by side, but one vast, reorganized megalopolis with a different character entirely, a giant elliptical galaxy. This analogy holds the key insight. In a galactic merger, emptiness is the rule, and the brilliant violence is reserved for the thin, luminous medium that fills that emptiness. It transforms an abstract simulation into a relatable story of atmosphere and architecture on a scale we can almost grasp. Yet, even as we comprehend the mechanics, a deeper question lingers about our own tiny place within this vast reorganization. This cosmic forecast places us in a moment of profound and fleeting privilege. We exist in a narrow sliver of cosmic time, a golden window that is uniquely perfect for witnessing this story. Look up on a clear night, and you can see the Andromeda galaxy with your own eyes as a separate, distinct smudge of light. In a few billion years, that will no longer be possible. The merger will have progressed too far, the two galaxies blending into a single, shapeless glow. Travel back in time several billion years, and the situation is equally blind. The galaxies would have been so much farther apart, their mutual motion so subtle, that predicting a collision would have been impossible. We are positioned by sheer cosmic accident in the sweet spot. We have the front row seat, the program notes in hand, just as the overture is beginning. It is a temporary vantage point granted by the slow, patient clocks of the universe, one that will close for every civilization that comes after the merger is complete. This timing is not just convenient, it is essential to our very understanding of galaxies as dynamic, evolving entities. Our ability to measure Andromeda's blue shift, to detect its sideways drift, and to compare it to other merging galaxies across the universe all depend on our placement in this specific epoch. We are like historians who arrived at the archive the very day the most important documents were laid out on the table, perfectly legible and complete. This fortunate alignment invites a deeper question, one that straddles the line between astronomy and philosophy. Does our ability to comprehend a future so distant it holds no consequence for our species carry any meaning? Some thinkers argue that it represents one of the most profound triumphs of the human mind. We are fleeting creatures living on a speck of rock, orbiting a middle-aged star in the quiet suburb of a spiral galaxy. Our individual lives are measured in decades, our civilizations in millennia. Yet, through patience, reason, and collective curiosity, we have pieced together a narrative that spans billions of years. We have decoded the silent language of starlight to predict the fate of our entire galactic home, an event that will unfold long after every mountain on Earth has eroded to dust. This is not a practical skill for survival. It is an act of pure understanding, a testament to a desire to know our place in the story, no matter how small our chapter may be. In that sense, our prediction of Milkdromeda is more than an astrophysical forecast. It is a message we are sending to ourselves across the abyss of time, a declaration that even within our brief moment of consciousness, we can perceive the grand arcs of cosmic history and find a strange, humbling beauty in our own transience within it. The certainty of Milkdromeda is more than a fascinating forecast. It stands as one of the most profound validations of modern science itself. This prediction is not a lucky guess. It is the direct result of centuries of accumulated knowledge, from Newton's laws of motion to Einstein's theory of relativity, applied with staggering precision across a void of 2.5 million light-years. To measure the sideways drift of a galaxy is to measure the width of a coin from a distance of 10,000 miles, and we have done it. This achievement demonstrates that the same physical laws governing a falling apple here on Earth also orchestrate the billion-year dance of galactic titans. It confirms that the universe is comprehensible, its future in many ways predictable, even across timescales that dwarf the entire history of life on our planet. This single prediction provides astronomers with a foundational case study, a nearby template for understanding the chaotic process of galaxy evolution that shapes the entire cosmos. When we observe two distant galaxies merging in the early universe, we can now look to the detailed, measurable future of our own local group and see the same physics playing out, just at a different point in time. This bridges the vast gulf between the distant past and the far future, turning our own sky into a living laboratory for cosmic evolution. The quest to refine this grand prediction has been a powerful engine for technological progress. It demanded the creation of space telescopes like Hubble, free from the blurring effects of Earth's atmosphere, capable of holding their gaze fixed on a single patch of sky for years. It pushes supercomputers to their limits, running simulations of billions of interacting particles to model the subtle gravitational tides. This drive for precision continues today with missions like the European Space Agency's Gaia spacecraft. Gaia is not looking at Andromeda. It is performing a monumental census of our own galactic backyard, measuring the position, distance, and motion of over 1 billion stars within the Milky Way with exquisite accuracy. This map is like taking a single, ultra-high-resolution snapshot of a swirling crowd. By understanding the precise motions of stars in our galaxy today, including those that are remnants of past mergers, we refine our models of its total mass and gravitational structure. This, in turn, sharpens our understanding of the gravitational forces at play when Andromeda arrives, allowing us to predict the dance steps with even greater confidence. Each new data point from Gaia and future observatories is a brushstroke in a clearer portrait of our inevitable future. The story of Milkdromeda, therefore, is a testament to human curiosity and ingenuity. It shows that by patiently decoding the light from the cosmos, we can extend our vision across unthinkable spans of both space and time, transforming the silent night sky into a narrative of breathtaking scope. A galaxy does not explode. The most persistent myth about our future merger is a spectacle of stellar fireballs and planetary annihilation, a vision popularized by dramatic artwork and science fiction. This imagery is powerful, but it is fundamentally wrong. The reality is far more subtle and, in its own way, far more magnificent. The emptiness of space is the great protector. If you reduced every star in the Milky Way to the size of a grain of sand, the average distance between them would still be over 4 miles. When two such sparse collections pass through one another, direct impacts are astronomically unlikely. The true violence is reserved for the thin veils of gas between the stars, which ignite in brilliant but localized bursts of creation, not destruction. This process is not a sudden crash, but a slow gravitational entanglement that unfolds over timescales longer than the current age of our planet. The term collision itself feeds this misconception. Astronomers often prefer merger or interaction, words that better capture the graceful, drawn-out gravitational dance between two vast, mostly empty structures. Another common error is the sense of imminence. We speak of 4.5 billion years as a certainty, which it is, but human intuition struggles with such a span. If the entire history of Earth were a 24-hour day, the merger would begin just as the next day is dawning. Our sun will have transformed into a red giant and faded long before the final act. This event is not in our future, it is in the galaxy's future, a reminder that cosmic and human timelines operate on profoundly different scales. Dispelling these myths is not about diminishing the event's grandeur. It is about refining our awe, understanding that the merger is a slow-motion renaissance of star birth, not a cataclysm of death, allows us to appreciate the true narrative written in the motions of Andromeda and the Milky Way. It is a story of transformation and renewal on the grandest possible stage, a testament to the dynamic, evolving nature of the universe we are so fortunate to observe and comprehend. Astronomers possess a remarkable time machine, not for traveling forward, but for observing our own future from a safe distance. Across the universe, other pairs of galaxies are currently locked in the same gravitational embrace that awaits the Milky Way and Andromeda. These cosmic laboratories provide a real-time preview, allowing us to witness the stages of a merger from start to finish. We see the graceful arcs of tidal tails, the brilliant knots of starburst activity, and the gradual blurring of spiral structure. Each of these distant interactions is a chapter in a universal instruction manual, and by reading it, we can decipher the specific fate of our own galactic home. Consider the Mice galaxies, a pair known formally as NGC 4676. Through the lens of the Hubble Space Telescope, they appear as two distinct spiral disks connected by a long, luminous stream of stars and gas. This spectacular tale is a direct result of their first close pass, a gravitational pull so strong it has drawn out the very material of the galaxies themselves. They are currently in a phase analogous to what the Milky Way and Andromeda will experience in their initial encounter. The mice show us the beautiful, destructive process of tidal forces in action, confirming that the elegant distortion we predict for our own future is not just theory, but a common cosmic occurrence. Another profound example is the pairing known as ARP-142, often nicknamed the penguin and the egg. Here, the interaction is more advanced. What was once a classic spiral galaxy, the penguin, has been dramatically reshaped by its smaller companion. Its spiral arms are now stretched and distorted into a shape that resembles a celestial bird, while the egg remains a more compact, dense elliptical. This system illustrates a later stage where the identities of the original galaxies begin to dissolve into a new, singular form. The intense, pinkish glow at the penguin's heart is a telltale sign of rampant star formation, a starburst ignited by the collision of interstellar gas. Observing this tells scientists that the violent fate of gas clouds and the subsequent firestorm of stellar birth are not unique predictions for Milkdromeda, but standard features in the merger playbook. By measuring the light from these systems, astronomers can quantify the frenzy. They can calculate how much gas is being converted into stars, how quickly the stellar populations are changing, and how the energy from supernova affects the remaining material. This data is then fed directly into the supercomputer simulations that model our local group. When the virtual merger in the simulation produces tidal tails and starbursts that match the real-life observations of the mice or the penguin, it gives researchers immense confidence. It means the physics encoded in their models is correct. It means the forecast for our own peaceful stellar passage and violent gaseous collisions is not a speculative story, but a reliable extrapolation grounded in observable reality. These distant analogues assure us that the future of Milkdromeda, while distant, is already written in the sky, playing out in countless other places across the cosmos. The thin, delicate veils of gas drifting between the stars are where the galaxy's future is truly forged. This interstellar medium, often pictured as serene nebulas, will become the most chaotic and creative theater of the entire merger. When the immense gas clouds of the Milky Way and Andromeda slam together, it is not a simple, uniform compression. It is a collision of atmospheres on a galactic scale, generating forces of almost unimaginable turbulence. Picture the most violent storm you can conceive, then multiply its energy by a factor of billions and set it across a volume of space spanning tens of thousands of light years. Within that chaos, supersonic shock fronts race through the gas, ripping it into intricate filaments and collapsing pockets simultaneously. Magnetic fields, normally faint threads woven through the galaxy, are caught in this turmoil. They become stretched, twisted, and amplified like strands of cosmic taffy until they are strong enough to influence the very paths of the collapsing gas clouds, guiding the birth of new stellar systems. This frenzied environment does more than just make stars. It becomes a powerful natural accelerator. Charged particles, mostly protons and atomic nuclei, can become trapped and propelled by these amplified magnetic fields and shock waves, gaining velocities approaching the speed of light. We call these particles cosmic rays. A merger like the one awaiting Milkdromeda would act as a colossal engine for such high-energy radiation, flooding the newborn galaxy with an invisible hail of atomic shrapnel. This radiation plays a subtle but critical role in the chemical life of the galaxy. It helps drive complex reactions in the dense clouds of gas, potentially influencing the formation of more elaborate molecules, the precursors to the chemistry of life. But the primary source of new elements remains the stars born in the violence. The most massive of these stars live short, brilliant lives and die in supernova explosions. Each detonation is a titanic forge, creating elements like silicon, oxygen, and iron, and blasting them back into the turbulent medium. This enriched gas then swirls into the next generation of collapsing clouds. In this way, the merger acts as the last great period of chemical enrichment for the combined stellar population of both galaxies. The oxygen we breathe and the iron in our blood were created in similar cosmic environments long ago. Yet this brilliant, productive frenzy contains the seed of its own end. The starburst is a spectacular but wasteful feast. The same supernova that enriched the gas also unleashed devastating shock waves and torrents of stellar wind. These forces act like a galactic hurricane, violently sweeping the remaining gas out of the star-forming regions, either blowing it entirely out of the galaxy or heating it to such extreme temperatures that it can no longer cool and collapse. The raw fuel for making new stars is, in cosmic terms, rapidly consumed and scattered. After several 100 million years of furious activity, the gas reservoirs are depleted. The brilliant blue glow of young star clusters fades as the massive stars die off. What remains is the longer-lived population of older, cooler, redder stars. Their collective light gives the now quiet elliptical galaxy its characteristic reddish hue. The galaxy enters a long, stable autumn. It is red because its star-forming days are over, and dead not in the sense of lifeless, but in the sense of a finished work. The major construction has ceased. The last great episode of chemical evolution for the vast majority of its stars is complete. The galactic system settles into a new, enduring equilibrium, its structure and composition now fixed for eons to come. This quiet legacy raises a final, humbling question about our own place within this slow-moving epic. The final, silent signature of the merger will be written not in light, but in the very geometry of the cosmos. As the supermassive black holes at the hearts of our galaxies spiral toward their ultimate union, they will perform a dance that warps the universe around them. This motion generates gravitational waves, ripples in the fabric of spacetime itself. Think of the smooth, two-dimensional surface of a trampoline. If you place two heavy bowling balls on it and set them spinning around each other, they will create ripples that travel outward across the fabric. Gravitational waves are like those ripples, but in the three-dimensional fabric of reality, propagating out at the speed of light. The energy lost to creating these waves is what slowly drains the orbital energy of the black holes, causing them to spiral ever closer in a final, tightening embrace. For the merging of Sagittarius, a star, and its counterpart in Andromeda, this will be an event of staggering power. In the last few moments before they become one, the orbital speed will approach a significant fraction of light speed, and the final burst of gravitational wave energy released will, for an instant, outshine the combined light of every star in the observable universe. Yet, to our human senses, this cataclysm will be utterly imperceptible. It will be a silent symphony playing out in the dark. We will not see it, we will not hear it. We will need an entirely new kind of sense to perceive it. This is the frontier of a new astronomy, one that listens to the universe instead of looking at it. Future observatories are being designed for exactly this purpose. The Laser Interferometer Space Antenna, known as LISA, is a planned mission by the European Space Agency with NASA collaboration. It will not be a traditional telescope. Instead, it will consist of 3 spacecraft flying in a vast triangular formation, millions of kilometers apart, connected by laser beams. The concept is sublime in its precision. As a gravitational wave passes through the solar system, it will ever so slightly stretch and squeeze the space between these spacecraft. LIS, as lasers will measure these minute distortions, changes smaller than the width of a single atom over a distance of 1,000,000 miles. This sensitivity will allow it to tune into the low-frequency hum of supermassive black hole binaries like the one destined for Milkdromeda, hearing their final cosmic chirp. By the time our local black holes merge, we will have already listened to similar events in galaxies far, far away. Each detection provides a template, a sonic fingerprint of a black hole merger. By studying these distant events, astronomers are already building the catalog that will tell them exactly what to expect from the finale in our own galactic core. It confirms the physics, refines the models, and turns a theoretical prediction into an observed, universal phenomenon. This new sense of hearing the cosmos reveals a universe alive with vibrations from the most violent transformations, a hidden layer of reality waiting to be perceived. It means the story of Milkdromeda will not end with a fading light, but with a tremor in spacetime itself, a whisper sent out into the void that says, "Here, 2 giants became one." This inevitable collision is not an isolated event, but a chapter in a universal story of transformation. It reveals a fundamental truth, that galaxies are not the serene, unchanging islands they appear to be from our distant vantage point. They are dynamic, ever-evolving entities, and the primary engine of their change is the very process we have been detailing, the gravitational merger. These colossal interactions are the great catalysts for cosmic evolution, the moments of metamorphosis that sculpt the diversity of galaxies we observe across the universe. The journey from the elegant spiral disks of the Milky Way and Andromeda to the vast, quiet elliptical of Milkdromeda is a textbook example of this universal mechanism in action. It is a process that does 3 profound things. First, it fundamentally reshapes galactic architecture, stirring orderly disks into 3-dimensional swarms. Second, it triggers a brilliant but final burst of star formation that ultimately exhausts the galactic fuel supply, leading to a long, quiet era. And third, it feeds and merges the central supermassive black holes, anchoring the new galaxy with a single, more massive heart. This is not destruction, it is a life cycle. We can see the evidence of this process everywhere we look in the deep universe. The most massive elliptical galaxies we observe, those silent red giants sitting at the hearts of galaxy clusters, are almost certainly the products of repeated mergers over cosmic time. They are the end results of a history of collisions, each one adding stars, quenching star formation, and building up that central black hole. Our own local event is simply a late-stage example of this same cosmic sculptor at work, a final consolidation happening long after the universe's most frenetic period of assembly. This perspective connects our personal, local forecast to the grandest narrative of all. It tells us that the beautiful spiral we call home is a temporary phase in a much longer story. Its eventual merger with Andromeda is not a catastrophe, but a natural and necessary step in its evolution, a step that countless other galaxies have already taken. By understanding this single, upcoming event in our own backyard, we gain a key to interpreting the entire history of the cosmos, seeing in the distant, ancient light of other galaxies the same story of dynamic change and majestic transformation. This cosmic forecast carries a quiet, humbling weight beyond its scientific facts. It forces us to confront a fundamental truth of existence on the grandest scale, the principle of impermanence. We look at the Milky Way, this immense river of light that has arched over every human who ever lived, and we instinctively view it as a permanent fixture, an eternal backdrop to our brief stories. The certainty of its merger with Andromeda shatters that illusion completely. It reveals that even the mightiest structures we can perceive, these islands of hundreds of billions of stars, are not monuments. They are temporary patterns in an endless flow, beautiful configurations that arise, evolve, and are inevitably reshaped by the relentless forces of gravity and time. Our galaxy has a birth, a middle age, and a future transformation into something entirely new. It has a lifespan. This realization can be dizzying. It places our own fleeting moment, our individual lives, and even the entire history of our civilization within a context so vast it seems to diminish us to insignificance. Yet there is a counterweight to that feeling, a profound source of wonder. We are the part of the universe that has become conscious, and we are living in the specific, narrow window of time where this story is legible. We can see Andromeda as a separate entity, we can measure its motion, we can run the calculations and visualize the future collision. In 1 billion years, that will no longer be possible. The merger will be too advanced, the two galaxies blended into one. We exist in a moment of cosmic clarity, gifted with a front-row seat to the opening act of an epic that will unfold over eons we cannot inhabit. This privilege bridges the cold equations of astrophysics with a deeper, more personal reflection. It challenges the human tendency to see our world as static and encourages us to see ourselves as participants in a dynamic, unfolding narrative far grander than our own. The universe is not a frozen museum. It is a living, changing arena of constant creation and transformation, and our ability to understand even a fragment of its story is perhaps the most meaningful connection we have to it. The quiet humility we feel is not about our smallness, but about the breathtaking scope of the reality we are part of, and our unique capacity to witness its majesty. Their night sky would hold no clues to its own dramatic origin. For any civilization arising in the mature, quiet expanse of Milkdromeda, the astrophysics they develop would be built upon a profoundly different cosmic reality. Their entire observable universe would be a single, vast elliptical galaxy, floating in an ocean of perfect blackness, the brilliant tapestry of spiral and irregular galaxies we take for granted. The nearby members of our local group would have long since merged into their own giant or vanished beyond an unreachable horizon. Their science would begin from a place of profound isolation, a unified island with no neighboring islands in sight. To them, the concept of two distinct spiral galaxies gracefully interacting would be a theoretical abstraction, a possibility read about in ancient data archives, not an observable fact of their present universe. Their cosmic context would be one of solitude on a scale we can scarcely comprehend. This lonely vista would fundamentally shape their philosophy and their science, leading them to ask different questions than we do today. How would they ever piece together the violent, creative history that formed their home? The evidence would be subtle, written in the motions of ancient stars and the faintest whispers in the fabric of space itself. By studying the precise paths of the oldest stellar populations within Milkdromeda, their astronomers might notice something peculiar. Instead of all stars moving in the randomized orbits typical of an elliptical galaxy, they might find distinct streams or shells of stars, all moving in similar, coordinated ways. These would be the fossilized tidal tails and stellar streams from the merger, not yet fully mixed after billions of years. Like archaeologists finding pottery shards from two distinct ancient cultures mixed in a single dig site, these kinematic fossils would be the primary clue that their galaxy was assembled from two once separate entities. An even more profound line of evidence would come from listening to the universe. The crescendo of gravitational waves from the final merger of the supermassive black holes would have faded eons ago, a single chirp lost to the past. But the cumulative hum from billions of such mergers throughout cosmic history creates a permanent, low-frequency background, a gravitational wave background permeating all of space. With technology far advanced beyond our own LISA concept, future scientists might be able to detect this omnipresent rumble. Within that hum, they might, through painstaking analysis, isolate the statistical signature of binary black hole mergers from a specific epoch, correlating it with the estimated age of their galaxy's oldest stars. This would provide a second, independent witness to the ancient era of galactic assembly. Their greatest challenge, however, would be cosmological. Without any external galaxies to observe, how could they possibly discover the expansion of the universe, the cornerstone of modern cosmology? The redshift of distant galaxies is our primary evidence. In an isolated Milkdromeda, that evidence is gone. They might deduce expansion indirectly, perhaps by developing an exquisitely detailed model of stellar physics and realizing that the oldest stars in their galaxy appear slightly younger than the universe must be for their galaxy to have formed, a paradox that could only be resolved if the universe itself had stretched, altering the timescales of early stellar evolution. It would be a monumental intellectual achievement, a detective story with almost all the evidence destroyed. This speculative future serves as a powerful mirror, reflecting the unique and fleeting nature of our own cosmic moment. We live in a golden age of observation, a temporary window where we can still see the separate galaxies, measure their motions, and witness mergers happening elsewhere. We are positioned perfectly to understand not only where we are going, but also the dynamic, interactive processes that built the cosmos. Our night sky is a rich tapestry, a story book still being written, and our ability to read it is a privilege granted by a specific alignment of time and space. The inevitable loneliness awaiting Milkdromeda underscores that our current view is not the eternal state of the universe, but a specific passing chapter, one we are remarkably fortunate to witness and understand. The story of Milkdromeda is ultimately one of cosmic legacy. It reveals a universe where the grandest structures are not permanent monuments, but evolving characters in an endless narrative of gravity and time. Our journey through this inevitable future has shown us the precise science that maps it, from the blue shift in Andromeda's light to the gravitational whispers of merging black holes. We have seen that for stars like our Sun, the event is a peaceful relocation within a vast emptiness, while for the thin veils of gas between them, it is a catalyst for brilliant, fiery creation. This collision is not an end, but a transformation, a slow-motion ballet that erases two majestic spirals to paint a single, enduring elliptical galaxy across the canvas of our local universe. This understanding grants us a perspective that is both humbling and empowering. We are temporary residents of a galaxy that itself has a lifespan, yet we possess the unique capacity to comprehend its entire story, from its ancient mergers to its distant fate. We live in a privileged moment, a narrow window in cosmic time where we can still see Andromeda as a separate smudge of light and know it for what it truly is, a future partner in a dance that will one day unify the heavens. That knowledge reframes our place in the cosmos. We are not just inhabitants of the Milky Way, we are witnesses to its dynamic history and its unfolding future. The next time you find yourself under a clear, dark sky, look toward the constellation Andromeda. Find that faint, fuzzy patch with binoculars or simply with the knowledge of where it rests. The light that reaches your eyes tonight left that galaxy 2.5 million years ago, carrying with it the unmistakable signature of its approach. You are not looking at a static portrait. You are looking at a chapter in a story still being written, a promise of a future sky being drawn slowly toward us by the silent, relentless pull of gravity. This vision of deep time and cosmic change is one of the most profound gifts of astronomy. It allows us to see the universe not as a frozen backdrop, but as a living, changing arena of which we are a conscious part. If this journey into our galaxy's ultimate fate has captivated you, there are countless other mysteries waiting to be explored. Consider subscribing to continue uncovering the universe's greatest stories with us. And we would love to hear your thoughts. What does this galactic future make you wonder about? Share your reflections in the comments below.